I am the virtual teacher at Egnatia Career College. Today we'll teach ground fault circuit interrupters, arc fault circuit interrupters, transient voltage surge suppressors, and isolated ground receptacles, lighting fixtures and ballasts. This is video number 9. Ground fault circuit interrupters, arc fault circuit interrupters, transient voltage surge suppressors, and isolated ground receptacles. After studying this unit, you should be able to understand the theory of ground fault circuit interrupters, GFCI, devices. Explain the operation and connection of GFCIs. Explain why GFCIs are required. Discuss locations where GFCIs must be installed in homes. Discuss the Canadian Electrical Code, CEC, rules relating to the replacement of existing receptacles with GFCI receptacles. Understand the CEC requirements for GFCI protection on construction sites. Understand the logic of the exemptions to GFCI mandatory requirements for receptacles in certain locations in kitchens, garages, and basements. Discuss the CEC requirements for arc fault circuit interrupters, AFCIs. Understand CEC requirements for the installation of GFCIs and AFCIs. Understand and discuss the basics of transient voltage surge suppressors and isolated ground receptacles. Electrical hazards. The most important consideration in the installation of an electrical system is that it does not kill anyone. Many lives have been lost because of electric shock from an appliance or a piece of equipment that is hot. This means that the hot circuit conductor in the appliance is contacting the metal frame of the appliance. This condition may be due to the breakdown of the insulation because of wear and tear, defective construction, or accidental misuse of the equipment. The shock hazard exists whenever the user can touch both the defective equipment and grounded surfaces, such as water pipes, metal sink rims, grounded metal lighting fixtures, earth, concrete in contact with the earth, water, or any other grounded surface. This figure shows a time current curve that indicates the amount of current that a normal healthy adult can stand for a given time. Just as in overcurrent protection for branch circuits, motors, appliances, and so on, it is always. Code requirements for ground fault circuit interrupters, GFCIs. To provide supplementary protection against shock hazard, the CEC requires that GFCIs be provided for the receptacle outlets of dwellings in these situations. For all 125 volt, single phase, 15 or 20 ampere receptacles in bathrooms and washrooms. A Class A type GFCI protected receptacle is required within 1 meter of the sink, Rule 26-720, This receptacle, where practical, shall be located at least 1 meter, but in no case less than 500 mm, from the bathtub or shower stall. A bathroom/washroom is defined in CEC Section 0. For all 125 volt, 15 or 20 ampere receptacles installed within 1.5 m of a sink, GFCI protection is required. For exceptions, see Rule 26-704 and Appendix B. For 125 volt, single phase, 15 ampere receptacles located outdoors and within 2.5 meter of ground level, a Class A type GFCI protected receptacle is required. Accordingly, a GFCI protected receptacle is required for a receptacle that may be used for an electric lawn mower or trimmer, Rule 26-722. One receptacle shall be provided for each car space in the garage or carport, Rule 26-723b. And Rule 86-306 deals with receptacles for electric vehicle charging. In boathouses, all 125 volt, single phase, 15 ampere receptacles must have GFCI protection. The CEC does not require GFCI receptacles for the receptacle for laundry equipment, a single outlet receptacle that supplies a permanently installed sump pump, A single outlet receptacle that is supplied by a dedicated branch circuit located and identified for specific use by a cord-in plug connected appliance, such as a refrigerator or freezer. Habitable, finished rooms in basements. The receptacle installed in the ceiling of a garage and designed for the overhead garage door opener. The receptacle installed for a cord-connected appliance occupying a dedicated space, such as a freezer. A receptacle installed below the sink for plug-in connection of a food waste disposal. A receptacle installed solely for a clock. On a second-floor balcony, such as in a condominium or apartment. The CEC does not permit GFCIs to be used to protect circuits containing smoke alarms and carbon monoxide alarms. Section 68 gives the electrical requirements for swimming pools and the use of GFCI devices. See Unit 22. The CEC requirements for ground fault circuit protection can be met in several ways. The two most common types of GFCI protection are in the form of receptacles and circuit breakers. The circuit breakers are available in either single-pole configuration for 120-volt applications or double-pole configurations for 240-volt or 120/240-volt applications. This figure illustrates a Class A GFCI circuit breaker installed on a circuit. A fault or current of 6 mA, or more will shut off the entire circuit. For example, a ground fault at any point on circuit B20 will shut off the washroom and laundry receptacles together with any other devices that are connected to the outlets on this circuit. When a GFCI receptacle is installed, only that receptacle and downstream receptacles are shut off when a ground fault of 6 mA or more occurs. Upstream receptacles are not affected, regardless of the location of the GFCI in the circuit. It must open the circuit when the current to ground exceeds 6 mA, 0.006 ampere. A GFCI does not limit the magnitude of ground fault current. It limits the time that a ground fault current will flow. A GFCI does not provide protection against shock hazard should a person make contact with two of the normal circuit conductors on the load side of the GFCI. Example, line and neutral. This figure shows how a ground fault circuit interrupter operates. The GFCI monitors the current balance between the hot conductor and the identified conductor. As soon as the current in the identified conductor is less than the current in the hot conductor, the GFCI senses this imbalance and opens the circuit. The other figure shows the internal wiring of a GFCI. The imbalance indicates that part of the current in the circuit is being diverted to some path other than the normal return path along the identified conductor. Thus, if the GFCI trips off, it is an indication of a possible shock hazard from a line-to-ground fault. Nuisance tripping of GFCIs is known to occur. Sometimes this can be attributed to extremely long runs of cable for the protected circuit. Consult the manufacturer's instructions to determine if maximum lengths for a protected circuit are recommended. Some electricians advise using non-metallic staples or non-metallic straps instead of metallic to prevent nuisance tripping. Precautions for ground fault circuit interrupters. Unit 8 covers interrupting ratings for overcurrent devices. For life safety reasons, electricians and electrical inspectors should always concern themselves with the interrupting ratings of fuses and circuit breakers, particularly at the main service entrance equipment of a residence, condo, or apartment building. A GFCI receptacle also has the ability to interrupt current when a fault occurs. According to the Canadian Standards Association (CSA) standard for GFCI receptacles, the current withstand rating is 5,000 amperes, RMS symmetrical. So, unless the overcurrent protective device protecting the circuit that feeds the GFCI receptacle can limit the line-to-ground fault current to a maximum of 5,000 amperes RMS symmetrical, installation of any GFCI receptacles close to the main panel should be done only after a short circuit study has been made to ensure that the available line-to-ground fault current is 5,000 amperes or less. Without this precaution, the GFCI sensing and tripping mechanisms could be rendered inoperable should a line-to-ground fault occur. When the GFCI is called on to prevent injury or electrocution of a person, it might not operate safely. This is a very important reason for periodically testing all GFCI devices. Instructions furnished with GFCIs emphasize operate upon installation and at least monthly and record the date and results of the test on the form provided by the manufacturer. Never test a GFCI receptacle by shorting out line to neutral. The mechanism will be damaged and become inoperable. On single-phase systems, the line-to-ground fault current can exceed the line-to-line fault current. See Unit 8. Check fuse and circuit breaker manufacturers' current limiting charts to determine their current limiting ability. A GFCI does not protect against shock when a person touches both circuit conductors at the same time, two hot wires, or one hot wire and the identified wire. Ground fault circuit interrupter in residence circuits. In this residence, the receptacle outlets installed outdoors, in the bathrooms, on the kitchen counter near the sink, and specific ones in the basement are protected by GFCIs. These receptacle outlets are connected to the circuits listed in the panel schedule in Unit 8 and identified on the floor plans. Swimming pools also have special requirements for GFCI protection. These requirements are covered in Unit 22. Never ground a system neutral conductor except at the service equipment. Otherwise, the GFCI will be inoperative. Rule 10-210A. Never connect the neutral of one circuit to the neutral of another circuit. When a GFCI feeds an isolation transformer, separate primary and secondary windings, as might be used for swimming pool underwater fixtures, the GFCI will not detect any ground faults on the secondary of the transformer. Long branch circuit runs can cause nuisance tripping of the GFCI due to leakage currents in the circuit wiring. GFCI receptacles at the point of use tend to minimize this problem. A circuit supplied by a GFCI circuit breaker in the main panel could cause nuisance tripping if the branch circuit is long. Some electricians say 15 meter or more can cause nuisance tripping of the GFCI breaker. In older houses that were wired with knob and tube wiring or early forms of non-metallic sheathed cable, which did not include a bonding conductor, non-bonding receptacles were used. Rule 26-702-1 allows a bonding receptacle to be used to replace older non-bonding receptacles, provided the receptacle bonding terminal is connected to ground by one of these means. Bonding to the nearest metallic cold water pipe. Running a separate bonding conductor to the system ground. Connecting to a metallic raceway. Rule 26-702-2 also permits a bonding receptacle to replace an existing non-bonding receptacle if each replacement receptacle is protected by a Class A type GFCI, and no bonding conductors are extended from the receptacle to any other outlet. Rule 26-702-3. Feed through ground fault circuit interrupter. The decision to use more GFCIs rather than trying to protect many receptacles through one GFCI becomes one of economy and practicality. GFCI receptacles are more expensive than regular receptacles. You must make the decision for each installation, keeping in mind that GFCI protection is a safety issue recognized and clearly stated in the CEC. However, the actual circuit layout is left up to the electrician. This figure illustrates how a feed-through GFCI receptacle supplies many other receptacles. Should a ground fault occur anywhere on this circuit, all 11 receptacles lose power. Not a good circuit layout. Attempting to locate the ground fault problem, unless it is obvious, can be very time-consuming. Using more GFCI receptacles is generally the more practical approach. This figure shows how the feed-through GFCI receptacle is connected to the circuit. When connected in this manner, the feed-through GFCI receptacle and all downstream outlets on the same circuit will have ground fault protection. The most important factors to consider are the continuity of electrical power and the economy of the installation. A receptacle that is installed specifically for the washing machine in a combined laundry/bathroom is not required to be GFCI protected if this receptacle is located behind the machine and is not more than 600 mm above the finished floor. Rule 26-704, Appendix B. Caution: do not connect the freezer receptacle in the workshop or the refrigerator receptacle in the kitchen to a GFCI protected circuit. These devices are not required to be connected to a GFCI protected circuit, since any nuisance tripping of the circuit could result in spoiled food. The leakage current tolerances allowed by the CSA approach the minimum trip settings of Class A GFCIs, 4 to 6 mA. Nuisance tripping can shut off the power to the refrigerator or freezer. Coming home to spoiled food is not a pleasant experience. Identification, testing, and recording of GFCI receptacles. Rule 68068-5 requires warning signs to be placed beside switches that control circuits protected by GFCIs. The signs will alert the user to the fact the circuits controlled by the switches are GFCI protected, and will specify how often the GFCIs should be tested. Figure 9.2 shows the GFCI receptacle test and reset buttons, identified as T and R, is illustrated in this figure. Pushing the test button places a small ground fault on the circuit. If operating properly, the GFCI receptacle should trip to the OFF position. The operation is the same for the GFCI circuit breakers. Pushing the reset button will restore power. The detailed information and testing instructions are furnished with GFCI receptacles and GFCI circuit breakers. Monthly testing is recommended to ensure that the GFCI mechanism will operate properly if a human being is subjected to an electric shock. Will the homeowner remember to do the monthly testing? Will the homeowner recognize and understand the purpose and function of the GFCI receptacle? Should all of the bathroom GFCI protected receptacles be identified? Will the homeowner recognize if a receptacle is protected by a GFCI circuit breaker located in an electrical panel far from the actual receptacle? These are important questions and a possible reason why CEC requires identification, and why the CSA requires detailed installation and testing instructions to be included in the packaging for the GFCI receptacle or circuit breaker. Instructions are not only for the electrician but also for the homeowner, and must be left in a conspicuous place so that homeowners can familiarize themselves with the receptacle, its operation, and its need for testing. This figure shows a chart the homeowner can use to record monthly GFCI testing. Replacing existing receptacles. The CEC is very specific on the type of receptacle permitted as a replacement for an existing receptacle, Rule 26-702. Replacing existing receptacles where bonding means exist. When replacing an existing receptacle where the wall box is properly bonded, E, or where the branch circuit wiring contains an equipment bonding conductor, D, the replacement receptacle must be of the bonding type, B, unless the replacement receptacle is of the GFCI type, C. In either case, be sure that only the bonding conductor of the circuit is connected to the receptacle's green hexagon bonding terminal. Do not connect the white grounded circuit conductor to the green hexagon bonding terminal of the receptacle. Do not connect the white grounded conductor to the wall box. The white conductor is the identified conductor and may be connected only to the identified terminal on the receptacle. Replacing existing receptacles where bonding means do not exist. When replacing an existing non-bonding type receptacle where the box is not bonded, E, and an equipment bonding conductor has not been run with the circuit conductors, D, four choices are possible for selecting the replacement receptacle. 1. The replacement receptacle may be a non-bonding type, A. 2. The replacement receptacle may be a GFCI type, C. The green hexagon terminal of the GFCI replacement receptacle is not bonded to ground. It must be left unconnected. The GFCI's trip mechanism will operate properly when ground faults occur anywhere on the load side of the GFCI replacement receptacle. Do not connect a bonding conductor from the green hexagon bonding terminal of a replacement GFCI receptacle, C, to any other downstream receptacles that are fed through the replacement GFCI receptacle, Rule 26-702-3. The reason this is not permitted is that if someone later saw the conductor connected to the green hexagon bonding terminal of the downstream receptacle, they would immediately assume that the other end of that conductor had been properly connected to an acceptable grounding point of the electrical system. The fact is that the so-called bonding conductor had been connected to the replacement GFCI receptacle's green hexagon bonding terminal that was not bonded in the first place. This creates a false sense of security, a real shock hazard. 3. The replacement receptacle may be a bonding type, B, if it is protected by a Class A type GFCI, C, Rule 26-702. The green hexagon equipment bonding terminal of the replacement bonding type receptacle, B, need not be connected to any grounding means. It may be left unconnected. The upstream feed-through GFCI receptacle, C, trip mechanism will work properly when ground faults occur anywhere on its load side. Ground fault protection is still there. 4. The replacement receptacle may be a bonding type, B, if a bonding conductor sized per Table 16 is run between the replacement receptacle's green hexagon terminal and a grounded water pipe or other effective bonding means. Rules 26-702-1 and 10-610. The acceptable means of connecting the equipment bonding conductor to the water pipe is described in Rule 10-700. Ground fault protection for construction sites. Safety on construction sites is of paramount importance to workers and employers. Safety regulations such as Provincial Occupational Health and Safety Acts and the Canada Occupational Health and Safety regulations govern how certain aspects of a building's construction will be completed. Temporary lighting and power are both referenced in the Acts and regulations. Along with the CEC, these determine the minimum requirements for the temporary wiring on a construction site. Because of the nature of construction sites, the continual presence of shock hazard can lead to serious personal injury or death through electrocution. Workers often are standing in water, standing on damp or wet ground, or in contact with steel framing members. Electric cords and cables are lying on the ground, subject to severe mechanical abuse. All of these conditions spell danger. GFCI receptacles provide protection for workers in the event of a ground fault. It is important that workers not attempt to bypass this protection. If the GFCI trips, it is an indication that there is a ground fault. The GFCI has just protected you from a ground fault. If you bypass the GFCI, you no longer have the protection offered by the GFCI. You may not get the chance to make the same mistake twice. This figure illustrates some portable GFCI devices that provide ground fault protection when plugged into non-GFCI receptacles. The permanent site office and any temporary lighting and/or power panels must fully comply with the CEC. They must be inspected by the Electrical Inspection Authority before connection can take place, Rules 2004 and 76002. Arc fault circuit interrupters, AFCIs. About 10% of fires are electrical fires. 1/3 of electrical fires are caused by arcing at poor connections or between conductors due to a breakdown in electrical insulation. For example, if the strands in a conductor of the cord for an electric iron break, a few strands may still be touching, and there may be enough of a path to permit current to flow. When the iron draws current, arcing will occur at the point of the conductor break. The current drawn by the iron will not trip the circuit breaker or fuse protecting the circuit but can develop intense heat at the break in the wire. Arcing faults can result from such things as poor terminations during installation, equipment failure, and the failure of conductor insulation due to circuit overloading or improperly sized overcurrent protection. This figure is an arc fault circuit interrupter circuit breaker that would be installed in the main panel branch circuit side. The current from a series arc follows the normal circuit path. Parallel arcing occurs between two conductors. The arcing may occur from line to neutral, or line to ground. Parallel arcing current does not follow the normal circuit path. How AFCIs work. An AFCI is designed to sense the fluctuations in voltage and current that may occur during an arcing sequence and de-energize the circuit if dangerous arcing occurs. AFCIs are designed to sense both series and parallel arcing and can distinguish between the arcing that occurs in the normal operation of an electrical system and the unwanted arcing that can lead to a fire. The arc that occurs when the filament of an incandescent lamp breaks, when a switch is turned on and off, or when appliances that are turned on are plugged into a receptacle are examples of things that produce arcs that are normally considered harmless. Installing and using AFCIs. AFCIs are required to protect receptacles except as per CEC Rule 26-656, 1 and 2. Installing an AFCI receptacle is similar to installing a GFCI receptacle. With a single-pole AFCI breaker, the white pigtail on the breaker is connected to the neutral bus in the panel, and the circuit conductors, black, hot, and white, identified, are connected to the respective brass and silver-colored terminals of the AFCI breaker. Some manufacturers incorporate arc fault protection and ground fault protection on a single breaker. If an AFCI detects a fault, unplug and/or disconnect all appliances connected to the circuit. Reset the AFCI. If the AFCI trips with the appliances removed from the circuit, this indicates a faulty AFCI breaker or a fault in the wiring system. Disconnect the wiring from the AFCI circuit breaker and retest the breaker. If the breaker still detects a fault, the breaker is faulty or has been damaged by the arc fault. Before replacing the breaker, perform an insulation test on the wiring system. If the AFCI is reset and it doesn't trip, reconnect the appliances that were connected to the circuit, one at a time. If the AFCI still does not trip, it is possible that you have a loose connection or that the arc cleared the fault. The installation of an AFCI device must conform to Rule 26-656. Performing an insulation test. An insulation test is normally performed with an insulation tester since it applies a voltage of around 500 volts to the system. If an insulation tester is not available, use your multimeter on its highest resistance scale. Follow all safety procedures. Turn off the power to the circuit. Isolate the wiring system from its source by disconnecting the wiring from the AFCI and disconnect all loads from the portion of the wiring system undergoing the test. It is best to remove all the loads on the circuit, particularly electronic loads. Isolate the ends of the wires at both ends of the run. Connect the insulation tester, megar, to the circuit. The resistance between the conductors should be 1 megohm or greater. Transient voltage surge suppression. In today's homes we find many electronic appliances, example televisions, stereos, personal computers, videocassette recorders, digital stereo equipment, microwave ovens, all of which contain many sensitive, delicate electronic components, example, printed circuit boards, chips, microprocessors, transistors. Voltage transients, called surges or spikes, can stress, degrade, and/or destroy these components. They can cause loss of memory in the equipment or lock up the microprocessor. The increased complexity of electronic integrated circuits makes this equipment an easy target for dirty power that can and will affect the performance of the equipment. Voltage transients cause abnormal current to flow through the sensitive electronic components. This energy is measured in joules. A joule is the energy of 1 ampere passing through a 1 ohm resistance for 1 second. In other words, a joule is the amount of energy used by a 1 watt load in 1 second. Hence, 1 watt-hour equals 3,600 joules. Line surges can be line to neutral, line to ground, and line to line. Transients. Transients are generally grouped into 2 categories. Ring wave transients originate within the building and are caused by welders, elevators, photocopiers, motors, air conditioners, or other inductive loads. Impulse transients originate outside the building and are caused by utility company switching, lightning, and so on. To minimize the damaging results of these transient line surges, service equipment, panels, load centers, feeders, branch circuits, and individual receptacle outlets can be protected with a transient voltage surge suppressor, TVSS. A TVSS contains one or more metal oxide varistors, MOVs, that clamp the transients by absorbing the major portion of the energy, joules, created by the surge, allowing only a small, safe amount of energy to enter the connected load. The MOV clamps the transient in less than 1 nanosecond, 1/1000th of a second, and limits the voltage spike passed through to the connected load to a maximum range of 400 to 500 peak volts. Typical TVSS devices for homes are available as an integral part of receptacle outlets that mount in the same wall boxes as do regular receptacles. They look the same as a normal receptacle and may have an audible alarm that sounds when an MOV has failed. The TVSS device may also have a visual indication, such as an LED, light-emitting diode, which glows continuously until an MOV fails. Then the LED starts to flash on and off. TVSS devices are also available in plug-in strips. One TVSS on a branch circuit will provide surge suppression for nearby receptacles on the same circuit. A practical approach in today's installation is to add a transient surge suppressor to your home's heat pump to aid in minimizing high voltage and spikes from the supply utility providers. This will add a longer life expectancy to the heat pump. Noise. Low-level non-damaging transients can also be present. These can be caused by fluorescent lamps and ballasts, electronic equipment in the area, X-ray equipment, motors running or being switched on and off, improper grounding, and so forth. Although not physically damaging to the electronic equipment, they can cause computers to lose memory or perform wrong calculations. Their intended programming can malfunction. Noise comes from electromagnetic interference, EMI, and radio frequency interference, RFI. EMI is usually caused by ground currents of very low values from motors, utility switching loads, or lightning, and is transmitted through metal conduits. RFI causes the buzzing heard on a car radio when you are driving under a high-voltage transmission line. This interference radiates through the air from the source and is picked up by the grounding system of the building. You can reduce this undesirable noise by installing an isolated bond receptacle, which will reduce the number of ground reference points on a system. Isolated ground receptacle. In a standard receptacle outlet, the green bonding hexagon screw, the bonding contacts, the yoke, strap, and the metal wall box are all connected together and bonded to the building's equipment grounding system. If you picture all of the bonding conductors in the building, you can see that many outlets could be connected to ground by multiple paths. In an isolated ground receptacle, the green bonding hexagon screw and the bonding contacts of the receptacle are isolated from the metal strap of the receptacle and also from the building's bonding system. A separate green insulated bonding conductor is then installed from the green hexagon screw on the receptacle connected to the bonding terminal of a device such that disconnection or removal of the device will not interfere with or interrupt the continuity of the bonding conductor. Rule 10-612-6. Lighting fixtures and ballasts. After studying this unit, you should be able to understand fixture terminology, such as type IC, type non-IC, suspended ceiling fixtures, recessed fixtures, and surface-mounted fixtures. Connect recessed fixtures, both pre-wired and non-pre-wired types, according to Canadian Electrical Code, CEC, requirements. Specify insulation clearance requirements. Discuss the importance of temperature effects when planning recessed fixture installations. Describe thermal protection for recessed fixtures. Understand Class P ballasts. Discuss the CEC requirements for track lighting. An electrician plans circuits that are economical without sacrificing the quality of the installation. For example, some electricians prefer to have more than one circuit feed a room. Should one circuit have a problem, the second circuit would still supply power to the other outlets in that room. Some electricians consider it poor practice to include outlets on different floors on the same circuit. Here, too, the decision can be a matter of personal choice. Some local building codes limit this type of installation to lights at the head and foot of a stairway. Residential lighting. Residential lighting is a personal thing. The homeowner, builder, and electrical contractor must meet to decide on what types of lighting fixtures are to be installed in the residence. Many variables, including cost, personal preference, and construction obstacles, must be considered. Residential lighting can be divided into 4 groups: general, accent, task, and security lighting. General lighting. General lighting provides overall illumination for an area, such as the front entry hall, bedroom hall, and garage. Accent lighting. Accent lighting provides a focus or accent on an object or area in the home. This might be recessed spotlights over the fireplace or track lighting on the ceiling of the living room to accent a photo, painting, or sculpture. Task lighting. Task lighting provides proper lighting where tasks are performed. In the residence in our blueprints, the fluorescent fixtures over the workbench, the lighting inside the range hood in the kitchen, and the recessed fixture over the kitchen sink are all examples. Security lighting. Security lighting generally includes outdoor lighting, such as post lights, wall fixtures, walkway lighting, and all other lighting used for security and safety. Security lighting is often provided by the normal types of lighting fixtures found in the typical residence. In this residence, the outdoor bracket fixtures in front of the garage and next to the entry doors and the post light might be considered to be security lighting, even though they add to the beauty of the residence. A visit to the showroom of one of the many manufacturers or distributors of lighting fixtures offers the buyer an opportunity to select from hundreds, in some cases, thousands of lighting fixtures. Most of the finer lighting showrooms are staffed with individuals highly qualified to make recommendations to homeowners so they get the most value for their money. The lighting provided throughout this residence conforms to accepted trade practice. Certainly, many other variations are possible. For the purposes of studying an entire wiring installation for the residence, all load calculations, wiring diagrams, and so on use the fixture selection indicated on the plans and in the specifications. Types of lighting fixtures. This unit provides an in-depth coverage of recessed fixtures commonly installed in homes. It also considers other types of available lighting fixtures. CEC Section 30 sets out the requirements for the installation of lighting fixtures. Although not involved in the actual manufacture of lighting fixtures, the electrician must meet code when installing fixtures, including mounting, supporting, grounding, live parts exposure, insulation clearances, supply conductor types, and maximum lamp wattages. The homeowner, interior designer, architect, or electrician has thousands of fixtures from which to choose. Specific needs, space requirements, and price considerations are among the factors to consider when selecting fixtures. It is essential for the electrician to know early in the roughing-in stage of wiring a house what types of fixtures are to be installed, particularly for recessed-type fixtures. The electrician must work closely with the general building contractor, carpenter, plumber, heating contractor, and the other building tradespeople to ensure that requirements for location, proper and adequate support, and clearances from piping, ducts, combustible material, and insulation are complied with during construction. The Canadian Standards Association (CSA) group provides the safety standards to which a fixture manufacturer must conform. Common fixture types are as shown in the table below. Important: always carefully read the label on the fixture. The information will help you conform to Section 30 of the CEC and complete a safe installation. The label provides such information as: for wall mount only, ceiling mount only, maximum lamp wattage, type of lamp, access above ceiling required, suitable for air handling use, for chain or hook suspension only, suitable for operation in ambient temperatures not exceeding grade Celsius. For line volt amperes, multiply lamp wattage by 1.25. Suitable for use in suspended ceilings. Suitable for use in non-insulated ceilings. Suitable for use in insulated ceilings. Suitable for damp locations, such as bathrooms and under eaves. Suitable for wet locations. Suitable for use as a raceway. Suitable for mounting on low-density cellulose fiberboard. For supply connections, use wire rated for at least grade Celsius. Not for use in dwellings. Thermally protected fixture. Type IC. Type non-IC. Inherently protected. The CEC, Part 2, and the fixture manufacturers' catalogs and literature are excellent sources of information. The CSA tests, lists, and labels fixtures for conformance to its standards and to the CEC, Parts 1 and 2. Recessed lighting. Recessed fixtures, in particular, have an inherent heat problem. Therefore, they must be suitable for the intended application and must be properly installed. To protect against overheating, the CSA requires that some types of recessed fixtures be equipped with an integral thermal protector. This device shuts the fixture off if it overheats, then resets once the fixture cools down. Because of the potential fire hazard when mounting lighting fixtures near combustible materials. Rule 30-200-1 states that fixtures must be equipped with shades or guards to limit the temperature to which such materials may be exposed to a maximum of 90 degrees Celsius. If lights are installed over combustible material, each fixture must be controlled by an individual wall switch if it is located less than 2.5 meters above the floor. Or if the fixture is not guarded so that the lamps cannot be readily removed or damaged. Rule 30-200-3. This figure shows a fluorescent fixture mounted on low-density cellulose fiberboard treated with fire-retarding chemicals to meet specific standards. All branch circuit conductors used for wiring a ceiling outlet box must have insulation approved to 90 degrees Celsius, example, NMD90. But their ampacity is derated to that of 60 degrees Celsius wire, Table 2, Column 2, Rule 30-408-2. This applies to most residential applications. CEC requirements for installing recessed fixtures. CEC Rules 30-308, 30-408, and 30-900 through 30-912 list requirements for the installation and construction of recessed fixtures. Of particular importance are the restrictions on conductor temperature ratings, fixture clearances from combustible materials, and maximum lamp wattages. Recessed fixtures generate a great deal of heat within the enclosure, making them a fire hazard if they are not wired and installed properly. This figure shows the roughing in box of a recessed fixture with mounting brackets and junction box. The branch circuit conductors are run to the junction box for the recessed fixture. Here they are connected to conductors whose insulation can handle the temperature at the fixture lamp holder. The junction box is placed at least 300 mm from the fixture, so heat radiated from the fixture cannot overheat the wires in the junction box. Conductors rated for higher temperatures must run in a metal raceway between the fixture and the junction box. This raceway must be 450 mm to 2 meter long. Any heat conducted from the fixture along the metal raceway will be reduced before reaching the junction box. Many recessed fixtures are factory equipped with a flexible metal raceway containing high temperature, 1508C, wires that meet the requirements of Rule 30-910-1. This figure illustrates clearance requirements for installing recessed lighting fixtures. Suspended ceiling fixtures. The recreation room of this residence has a dropped 13mm gypsum board ceiling. The fixtures installed in this ceiling are a lay-in fixture, suitable for recessed installation. In most residential applications, these fixtures would still be classified as recessed. And the CEC requirement of a minimum of 13mm clearance from structural members must be maintained, Rule 30-902. This figure shows the typical layout look at the suspended ceiling with the recessed light fixtures mounted. Support of suspended ceiling fixtures. When framing members of a suspended ceiling grid are used to support lighting fixtures, the grid installer must securely fasten all members together and to the building structure. All suspended ceiling fixtures must be securely fastened to the ceiling grid members by bolts, screws, or rivets. Most fixture manufacturers supply special clips suitable for fastening the fixture to the grid. The fixture must never be supported by the ceiling tile. Some inspection authorities interpret the intent of Rule 30-302 to mean that the recessed fixture must be supported independent of a suspended ceiling structure. This is usually accomplished by using a chain attached to the fixture and the building structure above the ceiling. Large fixtures such as fluorescents require at least 2 chain supports, which is a requirement of the National Building Code. The logic behind all of the securely fastening requirements is that in the event of a major problem, example earthquake or fire, the lighting fixtures will not fall down and injure someone. Connecting suspended ceiling fixtures. The most common way to connect suspended ceiling lay-in lighting fixtures is to complete all of the wiring above the suspended ceiling using normal wiring methods. EMT. Non-metallic sheathed cable. Armored cable. Or whatever type of wiring method is acceptable by the governing electrical code. With outlet boxes strategically placed above the ceiling near the intended location of the fixtures. Then make a flexible connection between the outlet box and the fixture. The flexible connection can be up to 2 meters long and is usually made by installing either of the following items. Flexible metal conduit with conductors suitable for the temperature requirement as stated on the fixture label, usually 90 degrees Celsius, Rule 30-910-1. Rule 12-1010-3 specifies that when flexibility is required. Flexible metal conduit does not require a clip within 300 mm of the outlet box except where the metal conduit is fished. And no lengths over 900 mm at terminals where flexibility is necessary. Armored cable containing conductors suitable for the temperature requirements as stated on the fixture label, usually 90 degrees Celsius. Be sure to staple the armored cable within 300 mm of the outlet box. It is necessary for the electrician who is installing recessed fixtures to work with the installer of the insulation to be sure that the clearances around the fixture are maintained. If the ceiling has insulation blanketing the fixture, it must be a Type IC fixture, Rule 30-906. When the only access to the junction box is through the fixture opening, the opening must be at least 180 cubic centimeter with no dimension less than 15 centimeters unless the entire fixture and junction box can be removed from the ceiling, Rule 30-910-5. Many small, low-voltage spotlights installed in today's homes do not meet this requirement. Therefore, an alternative access method would be required, such as through an attic. Or a removable fixture must be installed. Pre-wired fixtures do not require additional wiring. Rule 30-910-8 states that branch circuit wiring shall not be passed through an outlet box that is an integral part of an incandescent fixture unless the fixture is approved and marked for through wiring. For a recessed fixture that is not pre-wired, the electrician must check the fixture for a label indicating what cable insulation temperature rating is required. The cables to be installed in the residence have 90 degrees Celsius insulation. If the temperature will exceed this value, conductors with other types of insulation must be installed, Table 19 and Table D1. Ballast protection. A fluorescent ballast is a regulating component of the fixture which limits the current and provides the proper voltage to start the lamps. All approved fluorescent ballasts installed indoors, except simple reactance-type ballasts, for both new and replacement installations must have built-in thermal protection from the manufacturer. Ballasts provided with built-in thermal protection are listed by the CSA as Class P ballasts. Under normal conditions, the Class P ballast has a case temperature not exceeding 908 C. The thermal protector must open within 2 hours when the case temperature reaches 110 grades Celsius. Some Class P ballasts also have a non-resetting fuse integral with the capacitor to protect against capacitor leakage and violent rupture. The Class P ballast's internal thermal protector will disconnect the ballast from the circuit in the event of a high temperature. Excessive temperatures can be caused by abnormal voltage and improper installation, such as being covered with insulation. The reason for thermal protection is to reduce the fire hazard from an overheated ballast. Ballasts can overheat if they are shorted, grounded, covered with insulation, or lack air circulation. Fluorescent lamp dimming. In the case of compact fluorescent, even the lamps must be specified 4-pin instead of 2-pin, specifically to work with the dimming system. The fluorescent lamp is a negative resistive load that requires a ballast to control the electrical input for starting and maintaining operation. Dimming controls designed to reduce voltage input, as in the case of incandescent dimming, will extinguish the arc in addition to reducing lamp life. Fluorescent lamps can be dimmed from controls designed for standard magnetic ballasts, magnetic dimming ballasts, and electronic dimming ballasts. Like a low-voltage incandescent lighting system, a fluorescent dimming control must be matched to the technology for which it is specified. Standard magnetic fluorescent dimmers provide full-range dimming to 40% of rated lumen output. Magnetic dimming ballasts, available for only 30-watt and 40-watt lamps, can provide full-range dimming to 10% of rated lumen output. Electronic ballasts for dimming compact fluorescent lamps can provide full-range dimming to 5% of rated lumen output. Electronic dimming ballasts for long fluorescent lamps can provide full-range dimming to 1% of rated lumen output. To date, few manufacturers of long fluorescent dimming ballasts and controls offer reliable full-range dimming to 1% of rated lumen output. Several new manufacturers of fluorescent dimming ballasts and controls have recently entered the market, and several more are expected to come on the market. Lighting fixture voltage limitations. The maximum voltage allowed for residential lighting fixtures is 150 volts between a conductor and ground, rules 2 to 110 and 30, 102, 1. Rule 30 to 706 makes a further restriction in stating that, for dwelling occupancies, no electrical discharge lighting equipment shall be used if it operates with an open circuit voltage over 300 volts. Fluorescent and neon lights are examples of discharge lighting. Rule 30 to 706 addresses the increasing use of neon lighting for decorative purposes. Some important CSA and CEC requirements for installing recessed fixtures are summarized in this figure. LED versus CFL brightness. When considering energy-efficient lighting, electricians are sometimes asked which is brighter: compact fluorescent lights, CFL, or light-emitting diode lights, LED. CFL lights use a heating element to warm up and then ionize a gas inside a fragile glass tube. A high-voltage discharge is then used to cause the gas to fluoresce or glow. The gas inside the tube is often mercury vapor. When mercury gas gives off light, it is ultraviolet light that the human eye cannot see. To turn the light into visible light, a coating of phosphor is deposited on the inside of the glass tube. Phosphor glows white when struck with UV light, and this is what fluorescent light is. LED lighting uses semiconductor technology to make light without the requirement of heat as a precursor. The voltage on the circuit containing the LED is controlled such that the outer valence electrons in the semiconductor get excited to the point where they leave their orbital shell, but not so much that they can attain the next valence shell. The electrons are stranded between shells and must radiate their energy in the form of a photon so they can shed their excess energy and fall back down to their previous stable level. LED and CFL do not have a difference in brightness intrinsically. Brightness is determined by the amount of electromagnetic energy arriving at a point. The level of light in a room, in an underground garage, or under a street light is measured in lumens. A single CFL and LED bulb might have the same lumen, brightness, output but vary greatly in the amount of energy needed to generate that level of brightness. LED bulbs require much less wattage than CFL or incandescent light bulbs, which is why LEDs are more energy efficient and longer lasting. The far left of the chart is the lumens, brightness, of intensity, and the rest of the columns compare how many watts of power each light bulb type requires to produce that level of brightness. The lower the wattage needed, the better. Now compare the cost of a 60-watt replacement incandescent bulb to the other bulbs above. From 2016 rates, the average cost is 13 cents per kilowatt-hour in Canada. In the long run, the winner in the above comparison is the LED. In addition to LED's cost savings, government-backed rebates also exist in some scenarios for Energy Star products. This table provides a comparison of the various lighting options that are commonly used in Canadian households today. Warm white, WW, 9-watt compact fluorescent, and cool white, CW, 32-watt fluorescent strip lights are being compared to 40 and 60-watt incandescent and 9-watt 4000 Kelvin LED lights. 4000K LED lights are a very white, almost blue color of LED. Keyless luminaires are standard fixtures that are typical in areas which require light. They are made of plastic or ceramic material and use an A19 bulb. Keyless means that they require a switch to turn them on or off. A pull chain type requires constant power and the switch is the pull chain on the luminaire.